are Emmanuel and Yves, who will tell us about their experiences in hacking security cameras. So, welcome to you two.
Cool. Thank you very much. Welcome everyone to our talk, Say Cheese, How We Pwned Your Security Cameras. I'm really glad there's still so many people around, even though it's the last talk on the last day. I was afraid there would be an empty stage, so I'm really excited to see so many faces in here. So my name is Yves. With me is my colleague Emanuele. We're both working as penetration testers for a small company called Compass Security, based in Switzerland and Germany. And as part of our yearly research, we decided the last 2 years to spend this time to participate in the Pwned competition and successfully compromise 2 security cameras. And in the following 45 minutes, 50 minutes, we want to talk to you about, first of all, what's this Pwned competition, and then also walk you through how we exploited those 2 cameras. Now, for those that haven't heard, Pwned is a competition that's held by Trend Micro's zero-day initiative. So the goal is that they select a bunch of different targets, cameras among them, and they ask researchers to try to find 0 days in them and get code execution on those devices. You usually have like 10 weeks to analyze those targets, and then if you succeed, you can register for the on-site competition. If you succeed there as well, and you can demonstrate that you successfully hacked those devices, Trend Micro will buy your exploit. They will use it to improve their EDR, and they will also responsibly disclose it to the vendor of the product so they can fix it. So what's important? Well, in those 10 weeks before, you can do whatever you want. Once you're on site, there's a couple of rules. The first rule is that you have 3 attempts of 10 minutes maximum each. So if you find an exploit, it needs to be reliable and it needs to be pretty quick. The second rule you have is that there's no interaction. So you start your script and you're not allowed to do anything anymore. So you're not allowed to walk up to the device, unplug it, or press any button or anything like that. Next up, everything has to happen from an unauthenticated attacker. So you don't get any credentials, not even for a low privileged user, and if there's default credentials, they'll change them before you can attempt to hack this device and get code execution. And the last one that I want to mention is that devices will run the latest firmware. So if the vendor patches or updates anything the day before the competition, that's the firmware you have to attack, and that's the device you have to compromise. So yeah, keep in mind those 4 rules because they will become important later on when I talk about our journey. So in the competition that we participated, those were mostly devices that we could choose from. There were some printers, some smart speakers, cameras, some NAS devices, and also phones. Now, because that was the first time for us to participate, we decided to probably look at the devices that are seen as easier. So for example, if you are the first to successfully hack a printer, you would earn $20,000 or $30,000 for a camera. So we decided to buy a printer and a camera the first year to focus on those. In the end, we ended up spending most of our time looking at the Synology BC500 camera. Now, when you get this device, there's pretty much 2 things you want to initially do. You want to get some access to the device. Ideally, you want to have a shell on the device so you can analyze what processors are running on there, what ports are open. Maybe you can debug some processes to find if something works as you expected. The second thing you really want is to get your hands on the firmware so that you can use your favorite reverse engineering tools to look at them and hopefully find some vulnerabilities. So we're totally new to this, but when we received the camera, we unscrewed some screws, we opened it up, and we were greeted by those 4 holes. I myself, as a software engineer, I didn't know too much, but luckily we had some people in our team that were way more knowledgeable with hardware, and pretty soon they told me, well, obviously, that's UART. That's a serial protocol that you can talk with the device where you have some input and some output. So we soldered on a few cables, used our adapter, and then we could connect this camera to our laptop. Now when you start the camera, we could see like the boot log, and pretty soon we saw like a Linux boot log. So it's a Linux-based device. Once the boot finished, we were greeted by a login prompt. So obviously, we tried some default passwords, root, admin, Synology. Unfortunately, they didn't work. So we had to dig a bit deeper. What we did, using this UART connection, we could dump the firmware from the camera. So from the bootloader, we managed to just take all the memory blocks and dump them to our laptop. And we started to analyze, well, what could be the username and the password for this shell? Pretty soon we realized there's only 2 users. There's a root user and there's a Sino debug user. And after some more reverse engineering, we noticed that when you first set up this camera, you have a web interface where you create your own new account with a username and password so that you can then see your picture from the camera and everything. And that password that you choose there, that is also set for the Sino debug user. So knowing this, we now had a username and password, and we could log in to this camera. So we had the firmware, and we had a shell on the camera, and we could really start to analyze this camera and hopefully find some interesting bugs. So next up, we started to enumerate like the processes on this camera. We were looking at what was listening on some interface, on some port. And there was not too much. There were a few programs, but they didn't seem too interesting. The main one, the really big one, was the web server that was running on this camera. So as I mentioned, you could log into your web server, so you could see like the camera, you could change a few settings, and so on. But remember from before, in the competition, we won't have any credentials. So pretty much the only thing that was interesting for us were unauthenticated APIs, or maybe an authentication bypass. We spent quite a few days looking for a bypass. We didn't find anything, so, well, we just decided to go with the unauthenticated APIs. Now, one API that was very interesting was this language API. This was used to change the language of your camera. Normally, you would send a string like EN or DE or something like that to change the language, but we started to play around with it. So initially, just some random string, didn't seem to do much, but we pretty soon realized, well, actually it's sending this with content type JSON. So let's just try some more JSON-looking payloads, and what we soon after realized was that if we send something like foo here, in the response we see that some path, security info language, that's like also the path we have in the request, .foo is not exist. So something strange seemed to go on. So it seemed to look up this key or try to write to this key, and it couldn't do it. So no vulnerability yet, but like our spidey senses were like, something there is probably not quite right. So we kept on digging. Now at some point we decided, well, let's just send very long JSON keys, because why not? And interestingly, the server suddenly had returned a 500, so some server error, and we also saw like unexpected result from the CGI program, something was wrong. So this seemed to be quite interesting to us. So at that point, we decided to figure out, well, what exactly is the boundary where it crashes and where it doesn't crash? And what we saw, what was interesting with like 48 characters, it would not crash, but you would see this interesting output. Pretty much still the same error message as before, like 1, 2, 3, 4, 5 does not exist, but you see there's also a few bytes that are not printable. And to me this looked very interesting, especially some of them, like for example the lowercase v, that's like hex 76, it could be like some memory address. So this looked really like maybe we are leaking some program data, some program memory here. What was even more interesting is that when we connected to the camera using our shell, suddenly we had a lot of core dumps. So when we sent those long payloads, apparently that crashed some type of program. So at this point we were like really interested in what was actually going on here. Which brings us to the analysis phase. So we took some GDB server, put it on the camera, attached it to the web server, and again sent our long payload. And shortly after, we were greeted by something that looks like this. So we see somehow the stack got corrupted in libjansen. Libjansen is an open source library that's used to parse JSON object, and this libjansen is used by Sinocam CGI. This CGI, that's the one that's called by the web server to handle changing the language of the camera. So something here definitely went wrong. So after some more debugging and reversing, this was like what we found, this parse object function. And you can see at the bottom there's this scanf function. And what it does, it takes the key, that's the JSON key you're sending, it tries to find a space in there, and then it takes those two parts, before and after space, and tries to move them in the orange and green stack variables that are nicely named overflow 1 and overflow 2. As you might have realized, there's no bounds checking at all, so if you just send a really long JSON key, as we did before, we will start to overwrite some variables on the stack. So pretty much we have a classical stack buffer overflow here. Now, as libjansen is open source, we started to look at GitHub to try to figure out what's happening exactly. We looked at all version, all branches. This is nowhere in GitHub. That's not in the original libjansen source code. That's something Synology added later on themselves. We're not quite sure why they decided they needed JSON keys that can have a space in between. Don't know what's the reason for that, but that's something they decided to do, and that was great for us because now we had this stack buffer overflow. Now obviously the next thing you want to do is you want to look at the mitigations of libjansen to figure out what hurdles you have to overcome to later on successfully exploit this program. The first one for us, that was great for us, is there's no stack canaries. So there's no values we need to leak to overwrite the stack. Unfortunately, it's not the 90s anymore, so the stack was not executable. So this is one of the issues we'll have to overcome, that there's a non-executable stack. And the second challenge we have is that randomization is enabled. Pi, or like ASLR in general, is enabled on the camera. So we will have to deal with the randomization as well. And there's the third issue that we'll have to deal with that was less apparent in the beginning. But if you read the documentation of libjansen, you see that all your JSON that you're sending it has to be valid UTF-8. If it's not, it will refuse to parse it. What does that mean, valid UTF-8? Well, in the simplest case, in a 1 byte, it's the same as ASCII. You have your characters from 00 to 7F, and then everything above would be legal. Then you also have combinations, 2, 3, and 4 byte UTF-8 code points, where you have pretty much full flexibility on some bytes, but you're very restricted on others. But basically, what this means is, in the end, whatever our final payload will be, it has to be valid UTF-8, and we'll have to work around this. And this was actually probably the biggest challenge we faced when trying to exploit this camera. Okay, we found the overflow, we defined our issues. It's time to solve those issues and hopefully write an exploit. First of all, the probably easiest one to tackle, the non-executable stack. If it was like the 90s, very easy, right? In your payload, you somewhere send some shellcode, then you have your return address, you overflow this return address to point to your shellcode, and that will execute. Unfortunately, that won't work here, so what's usually the solution? The solution is to use ROP, return-oriented programming. You have your data, then you send some padding so that you can overflow the return address. Now, this proved to be more difficult than it usually is, because from where the overflow happened, this scanf, to where the first return was, there was quite a lot of function calls in between, so other functions that would be getting called. There was quite a lot of checks depending on other stack variables that we already overwrote, so it was very difficult to not crash before we actually reached one return. And we spent a few days or a few hours on this to find a solution. Luckily, later on we realized, actually, just after the return address, there's a nice function pointer lying around. And this function pointer will be called pretty soon after the overflow. So instead of just doing classical ROP and just overwriting the return address, we'd also overwrite this function pointer. So once the overflow happens, the program continues, it will pretty soon call this function. In an ideal world, we overwrite it with system. And what was really, really nice is that actually the first argument at that point in time would point right into our padding. So we could also just send the commands along. We just needed one address to overwrite. So this lined up perfectly. So with this, we can say, okay, first issue resolved. We know how to tackle this. Now the second issue is address space layout randomization, ASLR. So whenever a program is started, it's loaded at a different address. This was introduced exactly when someone wants to exploit it, that they don't know actually where those nice addresses of system are, and if you enter a wrong address, you'll just crash. Usually, to defeat ASLR, you want some leak, so that you know where the program actually resides. And if you think back, if we sent like a 48-character JSON key, we actually leaked some data. There's just one issue. This CGI that handled the language change, when this was started, pretty soon afterwards it was finished and died. And for every new request, a new CGI was spawned at a different address. So we could either leak an address, or we could do our overflow and write an address, but not both together. So we had to find some other solution. And after a while I was like, this is not like a modern computer. This is like an IoT camera running a 32-bit Linux. How much randomness is there actually? So I started to look, and we discovered there's 8 bits of randomness for each invocation. What does that mean? When you have an address like this one here, 1, 2, 3, 4, 5, 6, 7, 8, only 4 and 5 will be random for each invocation. What this means? Well, 8 bits of randomness, there's only 256 possibilities. So either we look like a really long time for a leak, or can we maybe just do brute forcing? For that, we had to understand the whole architecture a little bit better. So when we're sending a request, initially that's handled by the WebD. This one is the one that does authentication and checks if we can do that. And here we don't need authentication, so for changing the language, it will just spawn the Sinocam param CGI at some address, And if we didn't guess the right offset, it will just crash. But you could just keep going and going. And what's really nice here is it's only the Xenocam param CGI that crashes, not the whole WebD. Why is that important? Spawning this CGI, that was very fast, that was very quick. When the WebD, when we crashed that, sometimes that happened when debugging, it took like a really long time for the operating system to recover that. So like half a minute. So then it would not be possible. But because it was on the CGI, we thought like, well, it's not brute forcing question mark, but actually time for brute forcing exclamation mark. Let's do this. And what's really, really nice, as part of this, we can also tackle our UTF-8 issue at the same time. I'm going to show you how exactly we're going to do that. So let's say this is the address of system that we want to use to override this function pointer. X and Y, that's where the randomness will be. That will be randomized at each invocation. And first, what we have to pass is that this is a valid UTF-8. But what we can do is we can just choose X and Y in a way that in the end, if this as little endian encoding, that's why I have to switch, so that Y be 8X, so that Y and X just make this a valid 2-byte UTF-8 code point. And that should be possible. So we just have to choose those two values that this validation will pass. If this passes, our exploit will be passed to the vulnerable function, where most likely the offset won't align and will just crash. But no worries, we do the same. We stick with the same values that we chose. We'll always pass the UTF-8 validation and probably again crash. And we just keep doing that and trying that until hopefully at some point, by choosing still the same values, the program will actually be mapped where we hope it to be mapped, and at this point we successfully override that function pointer with system, and we should have our shell. Now, the address of system, and what we decided to choose X and Y, was this one here. So what's really nice, 76, that's a lowercase v, that's valid UTF-8. The green one, 34, that's just the number 4, also very easy, valid UTF-8. And 83dB, that can be encoded as the orange 06C3. So in the end, we had an address with, that we could encode as valid UTF-8, and with this, we were very certain that we can do this. Now, think back to the beginning. There's one more issue. We had like 3 attempts of 10 minutes each, right, at the competition. So, while in theory it's possible, can we actually do it within 10 minutes? So we did some quick napkin math, and we said, well, we need like at least 1,000 requests to be fairly certain that our exploit will work. So now the question becomes, how long does it take for one request? It takes like 100 milliseconds. So in 10 minutes, we should have like 6,000 requests. That sounds great. That's more than 1,000. So we said, well, ASLR UTF-8, fixed. We can do this brute force. We're good to go. Which brings us to our final payload, which was this. We just had some padding to nicely align everything. Then we had our, in red, the first part of our payload. This would unlock the root user. I'm going to explain in a second why. Then we would start telnet on the camera. We have some more padding with the Cs. And finally, the encoding of the system function that would override the function pointer. Why did we unlock the root user? Well, when actually looking at the camera, we noticed the root user was locked, but had a very, very strong password of 12345. So if we just would unlock the root user, we could then use root 12345 to log in via telnet to the camera and get a root shell on the camera. Now, unfortunately, reality was a bit different, as usual. So we started our brute force, started out with 100 milliseconds. But then, at some point, suddenly we encountered requests that would hang for a really long time, for like a minute. And once you had like one of those threads hanging, everything else became slower. And if you had more threads hanging, it became unbearably slow. So slow that we had no chance of succeeding, or like very little chance of succeeding in 10 minutes. Why does this happen? Well, pretty much there's not only 2 possibilities, but 3. So either you hit the correct address, you win. You hit some address that's not mapped and it just crashes. Or by mistake, you hit a valid address that's somehow mapped, but not the one you want. And if you hit that, either it probably was like an infinite loop that was happening there, or maybe it was some read function that expected some data that it never received, so it would just lead to this timeout. So we needed some solution for this, because otherwise we probably wouldn't succeed. And as usually, the solution was to reboot. But remember, we couldn't just walk up on stage, unplug the camera, and plug it back in. We needed some other way. What was very nice, while researching this and playing around, at some point we noticed that if we send a JSON key with exactly 185 characters, for whatever reason, one of the threads in the webd, so not in the CGI, but in the actual webd, would become stuck. And what we also noticed was that if all 10 threads of that webd were stuck, the watchdog would kill the webd and reboot the whole camera, because something obviously went wrong. So we could use that. We incorporated that into our exploit, that if we noticed the brute forcing was slowing down, we just spammed send this request to hopefully stall all the threads. The camera would kill itself, would reboot, and at that time we could brute force with full speed once again. Obviously, we lost a little time during the reboot, but still it was worth it, and we were way above the 1,000 requests that we needed. And this is how it looks like in the lab environment. We have like on the right the camera with the image, and on the left the exploit that I'm going to run. And you see it's just spam sending the request, which is brute forcing, sending and sending, until hopefully at some point we will hit the correct offset, which happened here. Now, when we hit that, unlock the root user and could log in, we decide to not just show we had code execution, but we actually downloaded our own web server and showed this nice new page for the camera, and finally also dropped into a shell as root on the camera. So we were very happy. It was a few days before the deadline, so we registered. We booked last-minute tickets to Toronto. A colleague and I, we were on the plane, and I had in-flight Wi-Fi. In the middle of the flight, I texted my colleagues in Zurich, "Everything is still okay, right? There's no new update." And soon after, they text me, "Well, actually, Synology just released a new update with minor bug fixes." This was me, so it was horrible. I was in the plane and was like, well, we probably land, we can take the next flight back home. So in Zurich, they rushed to install the newest firmware, to run our exploit again, and after like 15 excruciating minutes, I got a message that said it still works. So I was really relieved. So the next day, we went to the office from CDI. We successfully demonstrated our exploit. I was very relieved that we succeeded. Unfortunately, we were not the first team to use that exploit, so there's like a random drawing for a random order. So we didn't build the full prize money, but still, we were very happy that in the first year we tried this, we actually succeeded and managed to get unauthenticated code execution. And we liked this feeling so much that we thought, well, let's just do it again.
So, as my colleague said, after this positive experience, we decided to participate on the Pwned 2024. But this time, instead of targeting the Synology, we targeted the Ubiquiti because of the last day update. So we decided to try something else. That was one of the reasons, not only the reason. And so, as we did for the BC500, as soon as the target arrived, we bought it, it arrived, and we wanted to disassemble it in order to see all the internal interfaces that are available and try to get access to the firmware, as my colleague Yves said. But while we were unscrewing and opening the camera, we noticed that the camera maybe was not intended to be opened because it was not an easy task. It required like a lot of brute force that you can see on the frame of the camera. You can see that it's like a physical brute force, we can call it, in order to find like some hidden interfaces that we can maybe attach to. And after some times and after analyzing the motherboard, we were able to find the hidden interface. Basically, it's the only interface available that we were able to find in the motherboard was the Ethernet interface. So we decided, well, let's try to connect the camera to the network and see what kind of services are exposed. We attached the camera to the network, we ran Nmap, and we noticed that one of the services exposed was the SSH service. So we said, okay, we haven't set up the camera, so let's see if there are any default credentials. This time they were, and there was the default credential was UBNT. We tried to connect using those credentials, and we were successfully connected to the camera. So we tried to check the privileges of the users connected to the camera, and we were already root. So we already had like a root shell on the camera, and that's really useful for all the next steps. Then we used the same approach that we used for the BC500, so we tried to exploit any service that was exposing a port to the network. We found some crashes, but we weren't really able to just chain them and find the valid command execution. So we decided to try another approach. We read some researches from previous Pwned, and we noticed that the DHCP might be an attack vector. So we decided to check how the DHCP packets were handled by the camera. On the left side, you can see like a standard DHCP server on the network, and on the right side, you would see the camera. And basically, there is a binary running called UDHCPC, which is responsible to handling all the requests and responses associated with the DHCP protocol. So whenever the camera needs a new IP or needs to renew a lease, this binary will send the DHCP request to the DHCP server, and the DHCP response will be also handled by this binary. This binary will just extract all the information from the response and send it to another script called UDHCPC_CB. And in order to pass all the information from the response, it will just create some environment variables containing all the information read from the packet. This script will perform some actions, and at some point it will send a message to the inter-process communication inside the camera. That's because the idea is that other services might need this information related to changes in the network configuration. And the way that this message looks is basically a JSON file or a JSON object containing all the information retrieved from the DHCP response. So we decided to have a look at this script, and I didn't copy the entire code of the script because it's quite huge and couldn't fit inside the slides. But the only thing important in our case is that the IPC message is sent using the UBNT IPC CLI binary. And they are using different flags. You have the -m flags that specifies the message that needs to be sent via IPC. Then there is the -z flag that basically is just avoiding logging, but it's not important for us. And the -b is somewhat important because it means that this message will be sent broadcast, meaning that all IPC-enabled binaries will receive this message, and they can decide whether they want to process the message or just discard the message. So we noticed also that this script doesn't perform any escaping of the variables, and also, luckily for us, they don't perform any variable validation, meaning that we might be able to somehow control the message that is going to be sent. So we decided to analyze this part, and we decided to check the DHCP protocol to see if there are any limitations. And we found that, yes, indeed, there are some limitations. For example, we cannot really modify the IP field of the DHCP message because because the protocol limits it to be like 4 digits at most. So we cannot really send whatever we want. We need to find some other like fields that doesn't have so many limitations. And in our case, we were able to find a JSON injection. On the right side, you will see the standard JSON message that is sent on the IPC of the camera. And we decided to target the domain value because in the DHCP specification, it says that it can be any string. So we can use more characters. And we thought, okay, let's try to set the domain value to this value. The idea is that it should escape the domain JSON value and potentially inject an additional JSON key called IP with the value 8888. So we just created a test network with test DHCP server. We set the domain to this value, and we also used Wireshark to monitor the network, and we also monitored the IPC messages sent inside the camera. And at some point, we noticed that one of the messages sent was like this one. So the JSON injection worked. But now the question is, as you can see in this JSON message, there are two keys, two IP keys, one on the fourth line and one, the one in red. The question is which one will be considered by the binaries that are receiving this message. Luckily for us, and after some tests, we noticed that the last value is used if multiple values are present, meaning that we can overwrite all the other JSON keys that you can see in this rectangle. So we tried modifying some values like the IP and the subnet, because now we don't have the DHCP limitation anymore. We can just set it to whatever we want and see how other binaries are handling these values or these invalid values. But we couldn't find any real crash or anything that would lead to command execution. And then we noticed the first line, which is the function name, and we thought maybe that could be helpful. And we were like, okay, if the DHCP binary that is handling the DHCP protocol uses DHCP event as function name, what are other function name values of other binaries? So we started analyzing and reversing other binaries that uses IPC, and we noticed that, for example, the UBC system CFG binary uses adopt and change and VR settings function name. We continue analyzing other binaries as well until we notice this UBNT CGI binary that implements those function names, and also another one called reset to defaults, which from the name seems like interesting. But we also need to find like the full message required to trigger these actions, because, for example, let's say the test and apply network settings would also require, for example, the IP address, the net mask, and other information in order to be correctly executed. So we reverse the binary, this UBNT CGI binary, to identify the full JSON message required to trigger the reset to default action. And luckily for us, that's the JSON message and it needs to be sent. So we decided to write an exploit. And now I will show you directly the final logic because it's rather simple. Let's suppose that you have a network where the camera is attached and also the attacker laptop is attached to the same network. The exploit will first perform ARP spoofing on the camera in order to poison the ARP cache of the camera and tell the camera that the DHCP server now is the attacker-controlled machine. Then, when the lease time is going to expire, the camera will send the DHCP request, this time to the attacker-controlled machine, where a malicious DHCP server is running. This DHCP server will just answer with a DHCP hack packet, including the option 15 of the DHCP message, which is associated with the domain name. And the domain name value is the string that I just showed you before. And it's used to trigger the reset to default actions. Once the camera processed the DHCP message, it will perform a factory reset. And the script then tries to connect via SSH using the default credentials, and until the camera will just connect again to the network, the SSH service will just be running again, and then if everything is successful, the script will just connect via SSH. And now it's time for the demo, hoping that everything works. So here you should see the camera. And I'm pointing it to you because you should see some LEDs sometimes while it's like running or doing something. You should see some LEDs. And because of magic, it should be connected. And now I can check whether I have like a network connection to the camera. Not yet. Probably it's still running or booting. Okay. Now it's connected to the network. And now what I'm going to do is just executing the exploit, where I'm just providing... Sorry? Sorry? Sorry. Wait. Now it's better. Okay, sorry. So here I was just showing the ping command, and here I can just receive responses. And now here I'm just trying to execute the exploit, where I'm just providing the IP of the camera, the interface of this laptop, and the local IP of this laptop, and then some debug flags. When I start the exploit, you should see some information, debug information regarding the router IP and the camera IP and so on. Here it started the ARP spoofing and also started the DHCP server. And here you can see it was quite quick. We received the DHCP request from the camera. So we basically answered with the function, with the domain that I showed you before. And everything was stopped. And now you should see some LEDs on the camera at some point. And here the script is just waiting for a fixed amount of time for the camera to boot up again. And after some time, in theory, when the camera is still connected to the network, now you can see we were able to successfully connect to the SSH as admin. And as we did before for the BC500, we just uploaded a static web server and an index.html file that shows this page, and it also automatically opens the Firefox pointing to this page. That's basically the exploit. Okay. Okay, you can still see demo stuff. Okay, perfect. So after that, we had the exploit working. So we just registered to the event, to the Pwned event. We bought all the ticket, and we wanted to fly to Cork this time because they moved from Toronto to Cork, the competition. But considering what happened last year, the year before, that they released the update at the last day, we decided to create like a watchdog that would check the website of the vendor and notify us via email in case there would be a new firmware update. And we just landed at Cork. Like a few hours later, we received this email from the watchdog saying that a new release candidate was released. So as before, more or less, we did the same. We were a little bit panicked. So still in Zurich, the guys in Zurich just installed the update and checked that everything was still working. And a few hours later, we received also an email from the ZDI team listing all firmware versions that were in scope for the competition, and this new release candidate was not in scope. So we went for the competition, and also this time we were successful. And as it happened like the year before, we were not the first one hacking the camera, so we got a less bounty instead of the full bounty, but still it was a success. So after these two experiences, we have some takeaways that we would like to share with you. First, it's just to not be afraid to start, even if you feel unprepared. In the end, you will probably never feel totally ready for Pwn a new device, but we encourage you to start anyway. You will learn and figure out stuff on the way. Then also be persistent. We created this presentation, and you can see like logical progression of actions, but to be honest, sometimes it was a mess. It was not so linear. And we found a lot of dead ends. Some of them were not even a dead ends, but we thought it was a dead ends, but we still continue. So be persistent, and also be creative. Because to remember to test all services, also the one that doesn't really expose any port on the network, because they could still allow you to perform code execution. And spend some time testing and creating a stable version of the exploit, because in the end you have only 3 tries or 3 attempts, so more time you have spent stabilizing your exploit, more chances you have to be successful. And let's say, firmware updates usually drop at the worst time possible, as you have seen during the presentation. So be ready to just install the latest version, test it with your exploit, and ensure that everything still works. Of course, we have, since this presentation must be like 45 minutes long, more or less, we have to cut some details. But if you are interested, you can scan the QR code. It's not a phishing, it's just redirect to our blog posts, where you can read more details about the BC500 or also the AI Ballet, or even other like projects that we are doing. And that's all regarding the presentation.
Thank you very much. Are there any questions?
So I understood the release candidate was not in scope. Would it have changed anything?
Sure. No, we analyzed it. They didn't fix that. It was just Ubiquiti has like a cycle every couple of weeks, every month they release new firmware, and first it's a release candidate. It was for us it would likely just have been a normal release candidate and not something where they fixed any security vulnerabilities. On the other hand though, fun story, the Synology camera, where they said minor bug fixes, they actually were not that minor. They fixed 3 authenticated command injections. I know another team used them as part of their chain, and they had to become very creative. So they kind of hit this as minor bug fixes there.
Any more questions? No? Then thanks again. And see you all at 5 in track 1 for the closing.